very great pleasure this evening to welcome Dr. Caroline Villford from the University of Bath, telling us today about, I think, one of the most fascinating topics in astronomy and astrophysics. Certainly we're all fascinated by black holes. Caroline will be talking about supermassive black holes, and I think it's quite fascinating if you think about we're able to see these things in galaxies that are billions of light years away. That's what we will be hearing about tonight. And just very briefly, Caroline is very well known in the field for her work on galaxies and supermassive black holes. You've had the pleasure today to learn from her research and what she can tell you about that exciting science. Caroline did her PhD partly in Tokyo in Finland, but then moved on to the States, to this Space Science Telescope Institute, where obviously Hubble Telescope and JWST, the new telescope, is being built. Caroline then moved on to several places, the University of Florida. She spent some time at the University of St. Andrews, and then came as a senior lecturer, and is now senior lecturer at the University of Bath, in the department there. And yeah, she's an expert on supermassive black holes and galaxies. I'm sure you will hear lots of exciting things tonight. And thanks.
Well, thank you very much. Yeah, thank you very much for the invitation. So, as Sammy already said, today I'll talk to you about supermassive black hole and galaxy evolution. And this is my research, so this is what I study. And what I kind of want to convince you about at the end of this lecture is that supermassive black holes exist in basically all galaxies. And while they only have a tiny amount of mass, they can have a massive impact on the galaxies around them. And today I'm just going to try to explain to you why that is the case and what the black holes might do to the galaxies. But before we get to all of that, I think we should start with what we know about astronomy or astrophysics. And for most of us, that is that we've all gone outside and looked up at the night sky, and hopefully the weather was better than today, and we might have seen something much like this, which is our own Milky Way. And if we look outside on a dark night, what we see is mostly lots of little dots, and most of those will actually just be stars within our own Milky Way. This is the southern sky, so we see the imaginary clouds, but mostly, if we look out with our own eyes, what we see is stars in our own galaxy. So basically, all this beautiful picture here that we see is just a collection of something like this. So this is our own sun in a kind of more dramatic view, including high energy radiation. And basically, stars like that, like our sun, exist. They're massive balls of gas. There's fusion in the center that's driving them, and they can have masses around one solar mass, which is the mass of our sun, and maybe about 100th of that, up to 100 times the mass of the sun. And we'll just deal with masses in units of the mass of the sun. It's easier that way, so this is one solar mass. So all these stars make up galaxies. And so let's just look at a picture of a galaxy, and then we'll come back to that later again. So basically what you see now here is a galaxy. This is a spiral galaxy. Our Milky Way would look kind of similar to this. So basically what we see here is a rotating disk of gas and stars. So this is basically like a plate spinning about with a lot of stars in it. And in this case we also see, you see these little fluffy arms here in kind of darker, and there's blue little fluffy clouds around here. So what we see in this galaxy as well is a lot of gas clouds and dust, which are the darker bits, and those are basically the region in these galaxies where new stars are formed. So this is a galaxy built up of stars as well as gas and dust. And galaxies like this don't live in isolation, so we don't just have galaxies like that pinned somewhere in the universe sitting all by themselves. Galaxies live around other galaxies, and because they move around, they don't just live around other galaxies, they will at times interact with them. So what we see here now is two galaxies much like the one we've seen before. So you see, as you see before, you see this would be this nice little rotating disk. There's another galaxy here. What you see in this case is that those galaxies will have recently collided, and as they're colliding, they're basically ripping material out from the other galaxies, and they're interacting. They're having what we call a merger of galaxies. So galaxies don't live in isolation. They interact with other galaxies. That affects their properties. And often if we have a galaxy merger like this, what we might end up with is that the disks, those beautiful disks that we like so much, are destroyed, and we might end up with the kind of galaxies that astronomers like to hide from the public, which are elliptical galaxies. So this is a galaxy as well, and if you see pictures of galaxies, you will more often see the spiral type because they're pretty, whereas these ones are not that pretty. So what you see here, first of all, this is just a blob. You don't see those beautiful spiral arms with the dust lanes. You just see a blob of about uniform color throughout. There's another galaxy looking up there, but if you see this blob here, this is basically just a collecting of relatively old stars with nothing much in it. But this is a galaxy too. And until a few decades ago, if we thought about galaxy evolution, so the properties of the galaxies and the physics of how these galaxies evolve, how they form stars, we thought about those components I just talked about. We thought about all the stars, and the dust, and the gas, and the interactions. But that's not what I'm going to talk about today. So today I'm going to talk about a new player in galaxy evolution, and that is supermassive black holes. So far we haven't seen any supermassive black holes, so we're going to have to go and find one. So what I'm going to show you now is the detection of a supermassive black hole in the center of our own Milky Way. So what we're going to see is that basically at the center of all these galaxies we've seen so far, there's a supermassive black hole, and by supermassive I mean about 1 million to 1 billion times the mass of the Sun, which is a lot. Which is a scientifically accurate term, really. Okay, so let's find ourselves some supermassive black holes. So here what we start to see is a zoom into the center of the Milky Way. You might recognize this picture from what I've shown you before. So this is a picture you'd see if you look up on the night sky in the southern hemisphere. This is basically now we're sitting within one of those disk galaxies. That's where we live as occupants of Earth, and we're looking through this disk. And we're going to start zooming into the center of the Milky Way, which is about somewhere there. This is going to be a bit dizzying. That's going to go. Right. Okay, so we're going to start zooming in here. So we're now flying towards the center of the Milky Way. You'll see it will change view. We're flying towards the very, very center of the Milky Way. And with yet more and more stars, and soon we're getting to the end of it. And we're getting to the very, very center of the Milky Way here. And what we see here is a film taken over a bit more than 10 years by the Very Large Telescope in Chile. And basically what you see here is those stars like whizzing about. And what those stars in the very center of the Milky Way are doing is they're moving around a central mass. It's now helping you by drawing their orbits. And so what we're seeing here is that all those stars at the center of the Milky Way was found are moving around a single point. And because we know Kepler's law, so if you look at our own solar system, we can calculate the mass of the Sun from the orbits of Earth. The same way we can go to the center of the Milky Way, get out our physics books, and calculate the mass of the object by the orbits, so the periods and the 7 major, sort of basically the size of the orbit, and we can calculate the mass of the central object. And what we're going to get out for this is about a few million solar masses. And because we know the orbits of the stars, we basically know the maximum sizes objects can have. And it turns out that the only thing here that can explain those orbits without being observed is a supermassive black hole. And you see here this is a tiny, tiny scale, 2 or so light days. That's a bit larger than our own solar system. So that's really amazing. So what we see here is a supermassive black hole. So our Milky Way has a supermassive black hole. But our Milky Way is not alone. So in this case, we could calculate the mass of the supermassive black hole because we could directly measure the orbits. That is something, of course, that we cannot do in galaxies outside the Milky Way because this is already extremely challenging with the telescope we have on Earth. And once you place a galaxy a few 100 million light years away, you're kind of out of luck. But what we can do in those cases is basically just see that there's a lot of stars moving fast in the center, so we just see a bit more movement in the center, and from that we can calculate the mass of the supermassive black hole in galaxies other than our own. Okay, so there are supermassive black holes in galaxies. Now we can ask, well, how much do they contribute to the mass in the galaxy? So if we look at galaxies, and just here I found a picture of a different kind of galaxies just for variety. So if we look at galaxies like that, how much has the black hole contribute? So is the black hole basically half of the mass in the galaxy? Or what is it in this galaxy? And in this talk I'm going to basically ignore dark matter for the purpose of it and just talk about normal mass. So basically the majority of mass in the galaxy is in gas and stars. So if you look at a galaxy like that, mostly it's gas and stars. But the black hole have masses that range from millions to billions solar masses. So individually they're extremely massive. And they'll be more massive than any other individual component of the galaxy because all the stars are just really light. And irrespective of the mass of the galaxy, we find that a supermassive black hole contains about 0.1% or so of the mass in stars and gas and so on. So the black hole itself is extremely massive, but it's only a small part of the galaxy in terms of mass. So what I'm going to try and talk to you about today is basically, do we have to care about the black hole? So does the black hole matter to the galaxy? And what do I mean by that? So basically what I put up for you here is a classification astronomers use for galaxies, but mostly what it shows you is a lot of galaxies, and you see they have a lot of different shapes. A lot of them have arms, some of them don't. So basically, if we look at a galaxy population, they have a wide range of properties. Galaxies are not all the same. They're all very, very different. And so the question is, does the black hole matter for the fate of its galaxy that it sits in? So in a way, if I'm this galaxy here, or any of those galaxies, if the black hole were taken away and I'd lived my whole life again, would I look different? Or would I look the same? If the answer to that is you'd look the same, black holes would still be exciting. But of course, here we're going to basically ask, like, do they actually matter for the galaxies around them? So if we ask, do they matter, we can start with a simple question is, do they matter in terms of gravity? So basically, if we now ask ourselves, does the black hole matter for the life of its galaxy that it lives in? We can start with gravity. So if we go back to the picture of our galaxy, then think about, basically, if I remove the black hole, and I just think about the gravitational influence it has, does anything change for the galaxy? So I put up some numbers for you, and they're all approximate again, because galaxies have vast range of masses and sizes and so on, but just to give you an idea. So if you have a galaxy like that, the size will be tens of thousands of light years or so, so it's big. Like I said before, a lot of the mass is in stars and gas, and of course dark matter. So mostly it's stars and gas, dark matter, and so on. So what about the black hole? Again, I say millions to billions solar masses, and the black hole size is very small, much, much smaller than a light year. So if I drew the size of the black hole in here, you wouldn't see it at all. So one would naively think, well, but it's so massive, it should matter in terms of gravity. But we can ask ourselves basically, if I am a star in this galaxy, does anything change if I take the black hole away? And the way I can think about that is, well, if I'm any particle in this galaxy, I will feel gravitational influence of all the matter in the galaxy. And because that dominates, so if I sit out here, I will feel gravitational influence of the black hole, but I will also feel all the other material in it. So because it's such a tiny component of the galaxy, it actually doesn't really matter. And you could think about that if you want a non-physics one. Like if you have a massive party, and there's a person who has an extremely loud laugh, that person individually has the loudest laugh. But if you just hear everyone together, you kind of still don't hear the individual person. So basically, what we call the sphere of influence, the area over which the black hole dominates, over which your orbit would change if you remove the black hole, is extremely small. And by extremely small, I mean something like maybe only tens of light years or so. So in terms of gravity, the black hole, despite being so extremely massive, doesn't really matter at all. So the answer to this question is no. Does the black hole matter in terms of gravity? No, unless you're in the very center. It just doesn't. It's just not massive enough. Okay, but I still have a lot of talk to give. So how could it matter then? So if it's not gravity, how could the black hole matter for galaxy evolution? And this is going to sound at first a bit disturbing, which is the emission from around the black hole can matter. So black holes are not necessarily known for their emission. They're black holes. We know that they're so incredibly dense that not even light can escape. So black holes themselves do not emit radiation at all. But what I'm going to try to explain to you is that emission from around the black hole can matter a lot. So what I've put up here is an artist's impression of what we call an accretion disk around a black hole. That's a black hole in the center here, nice and black as you want it to be. And what you see here is something that looks in a way a bit like the disk galaxies that we saw. So what we have here is the illustration of an accretion disk. So in most cases, like our Milky Way, black holes just sit in the centers of galaxy and nothing really happens. We might have the stars moving around them like you saw at the center of the Milky Way, but otherwise they just sit there. But we do have cases in which gas clouds get near the center of a galaxy and they start to get disrupted and form what we call an accretion disk, and that's what we see here. So basically we have a gas cloud moving near the black hole, and it will start to get disrupted and form this disk. Now, in terms of orbits of material around the black hole, until you get very close, it's much like having any other kind of mass. So for example, if you had our solar system, you remove the sun, replace it with a black hole of the same mass, nothing would change. It just got dark, but we wouldn't change our orbits. So the black hole, if you had individual particles that were in stable orbits, they just stay there. But what we have in case of this accretion disk is the gas gets disrupted, and if it's dense enough, a lot of the material here can start to interact. So you basically have gas particles moving around it, and as they interact with each other, they start to heat up. And what we have is this disk of gas slowly moving material inwards, feeding it towards the black hole, thereby growing the black hole. Okay, but what I said, okay, and this heats up to high temperatures, so material at high temperatures emits thermal radiation, much like if you put something in a hot stove or so, it starts to glow, it emits radiation. The accretion disk does as well. So, but as before, we know the black hole, actually the mass is kind of minimal, so does this emission really matter? And for that, we'll try to see. So basically, if we think about the supermassive black hole here, it's grey because the background is black. But what I've drawn you on here is my best attempt of reproducing the gravitational potential of the black hole. So basically what we have here is material, and that's the distance from the black hole. So if we're far away from the black hole, we have high potential energy, and as we move closer and closer, that gets lower and lower, as we see here. Okay, why am I showing you that? The reason I'm showing you that is that as material moves closer to the black hole, we have to conserve energy, right? So basically, as we start here, if I'm a little particle starting here, if I start to move down here, and I'm going lower in the potential well, I have to transfer this energy, basically move it away in some way to conserve energy. Okay, fair enough. So basically, what happens then here is I have all this material in the accretion disk, and it starts to interact with other material in the accretion disk, and then starts to heat up the accretion disk. So all this energy here, as I'm going down the potential well, as I'm moving down and down here, starts to get transferred into the thermal energy of the disk. So it starts to be transferred into heat. So as I'm moving down here, all this potential energy here starts to go into the heat of the accretion disk. And of course, if material is hot, it will start to radiate. So basically then what happens is that if I'm a little parcel of gas here, and I move down here, some of my energy, because it will first get transferred into the heat of the disk, it will then start being radiated away. So I've just created some radiation. Fantastic. So if I'm a little parcel of gas moving out here, basically the amount of energy that I radiate would be proportional to how far I go down this curve. So a little bit of energy released as radiation. Fantastic. Okay, but that's nice. All right, so I can do that. But as you see here, this gravitational potential gets steeper and steeper as I get closer to the black hole. So once I get to the center here, the same step I take, a lot of energy starts to get released as radiation. Okay, so that's nice. And now you might think, well, that's all exciting, but we talked before about how, you know, the black hole in terms of gravity is not all that special because the orbits are the same. So I can say, well, this is a mechanism to build this accretion disk to release radiation. But then I could say, well, maybe, you know, the sun could do the same, or this desk or so if it were accreting. So why is this special? Why is this in any way special? Why can I not just say star here? So I just replace this with star here. So a star would have the same gravitational potential, and this is all like profoundly not to scale. So basically this is now no longer, well, this is still a supermassive black hole, but what I've drawn on here is now a star. So basically the difference for the supermassive black hole is that we have access to the very center of the gravitational potential because it's so incredibly compact. So the black hole now is special because it's compact. We can extract all of this potential energy here as radiation that we could not do for other sources. So other, say, a star or so, would simply not have access to this part of the gravitational potential to release all this radiation. So black holes are special in this way simply because they're so incredibly compact. And so they're fantastic machines for turning matter into radiation. How fantastic are black holes at turning matter into radiation, you may ask? It's fantastic. So if we think about like what we'd want what we'd want on Earth is fusion energy, so that's what's happening in stars, so you turn hydrogen into helium, that has a radiative efficiency, so basically what fraction of the rest mass gets turned into radiation, well below %, whereas the radiative efficiency of black hole accretion is around 10%. So if I throw this desk into it, about 10%, well, it would have to form an accretion disk, about 10% of its rest mass would be turned into radiation, and that is incredibly efficient. And it also can happen on quite short timescales. So in terms of radiation extracted from matter, black holes do matter, so they still only have a tiny fraction of the mass in the galaxy, but their ability to extract radiation from matter is extremely high. So an accreting black hole can, in fact, due to this incredible efficiency, outshine an entire galaxy. So what I'm showing you here is a galaxy. You might not see it very well. So if we have more amateur astronomers here, they might be well aware of these diffraction spikes. What we see here is basically a very bright point source, but this is not actually really a star. What this is a galaxy. It's kind of fluffy. You might see it if you just squint. But what this galaxy has is a supermassive black hole in the center that is currently accreting, and that has become so bright that it's much more luminous than the entire galaxy. And like I said before, it still has only a tiny fraction of the mass. So that stays the same. So I've spent a lot of my career trying to remove emission from the accreting supermassive black holes from galaxies. And it's fun stuff. And then you recover the galaxies, yeah. So basically, under here is a galaxy. And this is another example. So here we see this is a beautiful galaxy called Caroline 231. So this again is a galaxy where you have an accreting supermassive black hole that basically is brighter than the whole galaxy. Okay, so just to summarize this, basically if we play black hole versus galaxies, with the black hole not accreting, but we can say that the galaxy dominates both the mass and the radiation, right? This is the picture of our normal galaxy. If the black hole is off, we see nothing. We don't really see any effect of the black hole. But once the black hole is on, it dominates the radiation. And it can be up to about 100 times brighter than the galaxy. But the mass is still entirely dominated by the galaxy. So the black hole, ironically, can outshine galaxies. Okay, that's nice. So the black hole is now accreting, and there's a lot of amazing and wonderful physics that we see in this system where you have an accreting supermassive black hole, both off the accretion disk and around it. But today we wanted to talk about galaxies. Sorry. So now we can ask ourselves, well, that's all nice that this black hole is outshining the galaxy, but does it really matter? So basically we can ask, what effect does the radiation released from accretion have on the galaxy? And what I mean by that is that if you imagine that the galaxy just sits there and the black hole is creating all this radiation, if all of it just escapes out of the galaxy, well, it'll be more difficult to observe, as I can tell you. But it doesn't really change the life of the galaxy, it's just getting really bright at night. So, and then the way astronomers say that is basically, well, does the radiation couple to the galaxies? Basically, does it interact with the galaxy in any meaningful way? Or does it just all radiate away? And so, let's think about that. So to think about that, let's go back to some pictures of galaxies and see what components the galaxy has. Sorry. And how the black hole might interact with it. Okay, let's look at some pretty galaxies. All right, what do we have here? So what I put up here is a galaxy seen in different views. So if you first direct your view to the upper left, what we see here is basically existing stars, more or less, so that's the optical. So we see the usual view that we have. We see these little spiral arms here. We see the little lanes of dust. That's mostly existing stars, right? But as I said before, that is not the only component of the galaxy. So stars are part of the galaxy. But we also have fuel that can form new stars. So what we see here in orange, what you see in orange here and down here, the orange part of this, is far-infrared emission. Now, far-infrared emission basically traces cold, by which we mean well below freezing, or about 100 Kelvin or so, gas and dust. So you see here that besides all the existing stars, we have all these arms of gas and dust. And the reason we should care about is that it is this collection of cold material that will form new stars. So those galaxies are not dormant, so they don't just have the same population of stars all the time. They will form this gas and dust into new stars. And how do they do that? Galaxies can basically form new stars from gas and dust, but it needs to be relatively cold, because what we want the gas and dust to do is to collapse. If we heat something up, it will expand, so we want it to be quite cold. So the colder the better for star formation. And so if we look at galaxies like that, every location where we have cold gas and dust, there will be new star formation through collapse of those materials. And if we go back to those galaxies we've seen before, these blobby galaxies here, if a galaxy contains little cold gas or dust, it basically has no material to form new stars, so it will just stay as it is and form new stars. So what then is the effect of the supermassive black hole on this galaxy? Let's go through that. I've made some cartoons. So basically, we can now ask ourselves, like, what does the black hole do to? We can go through that. Stars in the galaxy. What does it in any way affect the stars in the galaxy? What does it do to gas clouds in the galaxy? And what does it do to cold gas in the galaxy? Is there some weird thing? Some weird sound? Or do I just hear that? I'm making this up. Okay, good. All right. And so I say here gas clouds in general, and then cold gas, and these are not entirely distinct. It will become clear from what I say why I separate them out. So basically, what does the accreting supermassive black hole do to those? We'll start with, quickly, just deal with that. Doesn't really do anything to the stars. I'll explain when I'm done. Mostly leaves the stars alone. But if we think about now, what does it do to the cold gas in the galaxy, which is symbolized by these little snowflakes here? Not because it's made out of water, just because that symbolizes cold. So if you have cold gas in the galaxy, remember cold gas is the region where you form new stars. And the gas has to be cold to collapse and form new stars. So what can the accreting supermassive black holes do to this? Well, remember, we're creating all this radiation. The black hole outshines the galaxy. And you can see the cold gas clouds a bit if you put out a snowman on a sunny winter day or so. Basically, it will start to melt because it absorbs radiation from the sun, not because it's hot around it. And something similar can happen to gas in the galaxy, where basically, if all these cold gas clouds start absorbing radiation from the supermassive black hole, they'll start to heat up. So remember, this cold gas that we see in galaxies forms stars. And if this radiation heats up the gas, it will basically stop it from forming stars, because it will be too hot to form new stars. So if we pump enough energy from all that radiation the black hole creates into the galaxy, we can heat up gas and stop the formation of new stars. So that's exciting. So we're starting to get to the point where the black hole might actually matter. But is this the only thing it can do? So it can heat up the gas, but it can cool down again, and it will cool down again. But it cannot really affect star formation in that way. So if you turn on the black hole in the center of the galaxy, we'd raise the temperature What does it do in general to gas clouds in the galaxy, which are now these little gas clouds here? So the other thing that, so I said before that, well, all this cold gas will absorb radiation, so it will start to heat up. So that's a bit like you sitting out on a sunny day and you'll feel the warmth from radiation. But it also does something else, and that is that all the radiation has momentum. So if I expose something to a lot of radiation, it will give it a little push each time it gets hit. So all this little gas cloud exposed to all the radiation from the black hole will start to get pushes from the radiation from the black hole. And the closest equivalent for that is basically a bit like a solar sail here. So if you build a solar sail, what you're trying to do is basically get all this transfer of the momentum from the radiation to accelerate your spacecraft or so. And the same thing can happen to gas clouds if they're exposed to a lot of radiation. So I can basically accelerate a cloud of gas by shining a lot of light at it. So if I have enough pressure from this radiation, I can accelerate gas clouds with the radiation from the black hole. And again, the black hole outshines the galaxy, so there's a lot of radiation to go around. And I'll actually show you that this might actually be happening in a second. Because again, so these are two mechanisms in which the black hole can actually interact with its galaxy. We still want to check that this is actually happening, that there's enough radiation to go around, but we'll do that in a second. If you just go back to the stars, basically the stars just don't have a lot of surface, so we don't really have a lot of interaction of the radiation with the stars to go around. But with those other methods I talked about before, so basically interaction of the radiation with gas in the galaxy, we can actually really affect the galaxy. And this is now an artist's impression. Basically, if we think about our galaxy here, so what we see here now is this grayish, blackish, with the blue dots in, would be a spiral galaxy. So if you have a spiral galaxies like this, and we have a supermassive black hole at the very center, and that would start to have, basically have one of those accretion phases and have a lot of radiation, what we could do is heat material in the center and also drive it out. So accelerate it to high temperatures to then be ejected from the galaxy. Now, velocity here matters. So if we think about it, basically, how would this affect the galaxy? This galaxy, as long as it has a lot of gas around, it can form new stars. So if I'm just kicking all the gas out, I have the possibility to stop it from forming stars in the future. But for that to work, I actually have to get this fast enough, because if I got my black hole to accelerate the gas, all the gas clouds to like walking speed, that possibly wouldn't do, right? That wouldn't escape the galaxy. So I want it at a high enough velocity that actually leaves the galaxy, doesn't come back, at least for a while. So is this something we see? And the answer to this is yes, this is something we see. So this will be a bit of a complicated plot. So basically, if we look at galaxies with accreting supermassive black holes, what we see is a lot of what we call outflows. So basically, in many cases, if we look, so here's the picture around the very, very center of the black hole, and we have the accretion disk here in the plane, and then you start to see material lifting out. So those are not actual pictures, those are artist impressions. But basically what we can observe around black holes is that we see material moving away from it. And if we look to the very center, some of that material can move at about 30,000 kilometers per second, which is about 10% the speed of light. Now that is very, very central, so this will not go far. But we clearly see that a black hole is capable of accelerating material to very high velocities. So this would be at the very, very center, extremely close to the black hole, almost like you're on light year scale. So that's fast. If we care about the galaxy, we don't really care about the central light year, so because that's small stuff. So we'd want the material to go faster, to go further. And of course it will start to slow down, it will start to collide with material around it. So if we start to zoom out, and now of a picture of the whole galaxy, we still have this very central region. But in many galaxies where we see accreting supermassive black hole, we see gas moving on larger scales, on galaxy-wide scales, and scales of the size of the galaxy, of up to about 1,000 kilometers per second. Now, since all of those velocities just seem mad, if we think about it again, what do we want the gas to do? 1,000 kilometers per second is just crazy fast on human scales. But for the galaxy, what we care about is basically, does the gas leave? Is it fast enough to escape the gravitational potential of the galaxy? And in these cases, if we get to those kind of velocity, it actually is. And not all of it will, but we clearly have the capability here of moving gas fast enough to affect the galaxy. So, kind of fascinatingly, what we have is a situation in which those wonderful galaxies here, with all the stars and gas and so on, can have this black hole in the center which has such a tiny fraction of the mass, again less than 1% of the mass in gas and stars is in the black hole, and yet it can affect the gas and stars in this incredible way and move it to these very high velocities, and thereby have the potential to affect its star formation. So that's exciting, because my talk had a point, and black holes actually matter in galaxy evolution because they can have an effect on star formation. I have to say one more thing about black holes, because it seems for completeness. So I talked a lot up to now and tried to explain how radiation from accretion can have an effect on galaxy, and how the extraction of the gravitational potential energy can really affect the galaxy itself. I have to mention for completeness, because that there's also, so if you remember that pictures I've shown you before, there's that blue swirly bit here. What that basically is another component of the black hole that can also affect the galaxy around it. So what we have here is that as the material is rotating, some of it will get wound up along these jets here, and that's basically, so they go both sides from the black hole. And these features here can move at basically the speed of light outwards into the galaxy as well. And that's what we call jets. And if we look at some galaxies here, so we see now a side-on galaxy, a disk of the galaxy here, we're looking into it like that. If you look at those giant lobes here, this is one of those jets. So they can travel to sizes much larger than the galaxy itself. And they do emit some radiation, but they basically also inject a lot of material into the galaxy around it. So the jets themselves can affect the galaxy as well. So there's two ways for the black hole to interact with the galaxy. So if we now think back to where we started from, and we ask ourselves, well, for galaxy evolution, do black holes really matter? What we nowadays believe is that they actually do quite a bit through those mechanisms I just explained. But the caveat to this is that all the physics I explained to you, so what I explained to you about both the jets and the radiation, is what we call AGN feedback, and it's actually something that's still not really understood. So we're still working out a lot of the physics and the details and what exactly it does to the galaxy. But it's a very exciting area of galaxy evolution. So if we finish the talk by having a look at some simulations. So if we now don't just think about a single galaxy that will have a black hole that every now and then will be on, and it will emit all the radiation, and it might change it. And we'll think about how galaxy populations as a whole evolve. We can start to see the role that black holes play in them. If we can. Oh yeah. So what I'm showing you here now is a simulation of the evolution of the universe. And this is starting. Can we just stop it for a second? Oh, nice. Well, that went bad. All right, so I was just going to, before it starts, I was just going to explain. So what I'm showing you here now is a simulation of an evolution of the universe. And that starts from the beginning of the universe about 13.5 billion years ago, and it just kind of whizzes through the whole history of the universe. And what you'll see towards the end is the effect of black holes, and that is something that is put into simulations to explain the properties of the galaxy population. And I will start pointing out when the black holes start to have an effect. So we start here at it's now very early in the universe, and what you see here is galaxies starting to form. So in the beginning you see here the distribution of matter in the universe is relatively smooth, and as time goes on you start to see it clump more and more, and so the turning bit is for the amusement of the viewer, not because that's what's happening. And so you start to see here these little blobs here start to merge, and that is simply galaxies forming. And so as the universe evolves, we see more and more these galaxies. You see that you start to get more and more concentrated. They have these interactions, and soon now what you start to see is this weird little flickering in some of the galaxies, like here now. Well, now it went boom. And now basically, so all the times it goes boom, this is basically where the simulations take this energy emitted from the black hole and put it into the galaxy. And you see how much this is affecting the galaxy. So what we see here is this process of the gas being blown out of the galaxies and distributed far and wide. So in galaxy simulation, this process really matters a lot. And then you see it here. So all the bubbles are basically phases of black hole accretion. The universe is now halfway over. It's getting a bit less dramatic soon. And then things will start to calm down a lot. So in all of those, so from our understanding of galaxy evolution, these processes I explained to you really play a rather large role for the pictures of galaxies we see nowadays. So if we go back to asking, like, what is the role of black holes in the fate of a galaxy, it's most likely quite a large one, despite the fact that it has such a tiny, tiny mass. And so basically, the black holes in a way are the underdogs of galaxy evolution, because you'd think they don't matter, but actually, they might just do. And for the students in the back, if you want to go into research, there's tons of stuff to do here, and you have wonderful people at Portsmouth working on this. Yeah. So think about black holes if you think about galaxy evolution, because they are important. Thank you very much.
Caroline, for this fascinating journey through the universe, through black holes. They're tiny but important, that's good to know. We've got one to in our galaxy. We've got quite a bit of time for questions, so please. So there was a hand up there first. Student of mine, well done.
How do you think that in the early universe, the kind of
will then expand. So because so there's not a lot of mass in the metal. They're very light, and also so the first black holes will have formed quite late. So this is way after inflation or anything, if that's what you were aiming towards. So it's way later. So we still don't quite know when the first black holes have formed. So those jets have an effect mostly on the large scale gas in the galaxy, but mostly by depositing energy, so again heating up the gas. So they don't really redistribute mass in the major way. So they don't have a major influence on the gas on the mass distribution, and therefore on the large scale they don't have an effect in that way.
There was a question here. Yes,
the radiation from the accretion disk, is it isotropic, and is it smooth radiation in spectrum wise?
So it's not isotropic. It's not isotropic for a few. So it's a disk. So that's always gonna have some anisotropy. There's also, so I didn't talk too much about the structure around the black holes. We also see around black holes that so you have the accretion disk, but then further out, as kind of an extension to the disk, you have what we call the dusty torus, which is just basically a Chinese donut. And that obscures a lot of the radiation. So in fact, often what we see in galaxies is that the radiation in those cases is kind of, it looks a bit like a bicone. So that's not a very good description, is it? So basically it will look like this in each direction. So basically, if you think about a donut trying to shine light of it, you'll basically have these triangles each way. So it's not isotropic. And in terms of you were asking about the wave, like what? The spectrum. And so because the spectrum is mostly, so the accretion disk, as you move inward, is basically will get hotter and hotter. So you basically have the sum of the thermal radiation at different radii. So a lot of those accretion disks, we see a lot of it in the X-ray, UV, optical, and it kind of gets, it drops off quite a lot.
It's not quantized.
What do you mean?
It's not quantized.
It's mostly, well, it's a sum of thermal radiation, yes. So well, you also have emission lines, but that's a whole other story. Yeah, so most of it is the accretion disk, and that depends on the temperature distribution in the disk.
Yes, you can go ahead if you have a question there.
My question is, dark matter, does it form part of the accretion disk? I can't think how it would, but what happens if dark matter falls into the black hole? Does it come out again on the other side?
So once it falls in the black hole, it's just in the black hole. So I think how exactly the dark matter, well, that's always terrible. So I mean, some of it will definitely accrete onto the black hole, but once it's accreted, there's no way out for it. So once it's accreted into the black hole, it just increases the mass of the black hole. So also the jets, they're not, so this is not coming out of the black hole, it's just from near the black hole.
So what would the mass of the black hole be dark matter?
Well, but it wouldn't matter because, yeah, it could, well, it could be, and some of it will be, but once it's in the black hole, you can't tell anymore. So once it's in the black hole, all you have is its mass and its spin. Yeah, but you will accrete dark matter onto it. Yeah.
Increases relative concentration of dark matter and water.
But I think again, because the fact is still that the mass in black holes is negligible overall. It's just in terms of mass, they don't matter. So in that sense, even if you have a slight imbalance of baryons and dark matter to accrete onto them, I don't think that would have a measurable effect on the fraction.
All right, we've got another question here.
Yes, sorry, it's a two-part question. We know that very large stars can create black holes when they die.
Yeah.
But do we know how supermassive black holes are created? And do we know what came first, the galaxy or the supermassive black hole?
No, but there are options. So in terms of like creating it, so they were most certainly not created at the masses there are. There are no processes we know of to create something 1 million solar masses as a black hole. So you have different options to basically create what we'd call a seed black hole. So in the early universe, you make a small black hole, and that in many cases might be more massive than the kind of black holes we create from supernovae. So that is because stars in the early universe is different because there's less heavy materials, so metals, what astronomers call metals, which is everything heavier than helium. There's different ways there to create what we call seeds. So that's either supernovae of more massive stars or other direct collapse. In both cases, that black hole will grow through the history of the universe. So we are very sure that whatever those black holes are here, that a lot of their mass was created during accretion phases. So once you accrete, of course, while some of the energy is radiated away, a lot of the material goes into the black hole, feeds the black hole, grows the black hole to the mass it is today. Where exactly the seeds are from we're not quite sure.
Yes.
Sorry, that gentleman's question was similar to mine. So while you say that the black hole could have formed from a disk of gas and dust in the early days of the galaxy formation, or is it more likely that it could have formed from stars in the centre of the galaxy, perhaps because there was presumably there was a lot of material in the centre of the galaxy in the way of stars? Could a black hole form from, say, several stars collapsing? Why are they in the centre of the galaxy, black holes? Not all, presumably, but I think you're saying that most galaxies will have a black hole in their centre.
Yeah, so in the galaxies, they're generally in the centre. If there are supermassive black holes, you have smaller ones around it. In terms of how they first formed, so as an observational astronomer, part of the challenge there is that the early universe is incredibly hard to study. So all these questions about how the first stars and galaxies formed are difficult to answer simply because we don't have a lot of observations of those galaxies. If you run simulations, basically if you place a black hole somewhere in the galaxy, it will basically move to the center through gravitational interaction. So the black holes kind of naturally sink to the center of the galaxy, which is why they're there.
Very interesting video at the end, but I understand that the universe expanded at the early days of its existence. What did it expand in?
Oh, I have this conversation so often with the physics colleagues I work in. Not into anything. I think that's a difficult question. So basically, it's the universe, it just expands, which is not really a satisfying answer, is it? Because like what it expands into is it.
The room wasn't there before.
Yeah, it doesn't really make sense. It's just it expands, and it hurts the brain, but it doesn't have anywhere to expand into because it's the universe. That's not great, is it? No, but for some reason it doesn't have a center because it's just itself and it expands.
All right, we've got another question from get the microphone there. So, Danny,
hopefully or just what's that question? So there's a limit which is realization where the universe is no longer. So there's at some point there will be the dark ages where photons or light can simply not travel through the universe. So that's kind of our hard limit. We've seen just before. What's the 12?
It's 400,000 years after the Big Bang.
Yeah.
It's basically 40 billion years that we look back.
Yeah. Is it 12? Is 400,000?
Yes.
Ah, okay. Yeah.
So we've seen radiation from 14 billion years. That's what I'm asking. I mean, like, the radiation takes time to get to us, and we can see what happened in the past, like further out away from us. So how far away from us we understand.
So we can see that was basically like 500,000 after the Big Bang. That's how far in time we can look back. Distance is a difficult concept if the universe is expanding, because when do you measure it? So any galaxy we see that whatever 400,000 after the Big Bang, its distance will not be the look back time in gigayears. It will now be further because the universe has since expanded.
So it appeared longer time ago than it was.
So the reason we know how long it is ago is because we have to put in a cosmological model, so that's actually not that simple. So you basically have to know how the universe expands, but then do the calculation to turn the distances you measure into time. So basically you can't just measure that, you have to have the model of the expansion of the universe. I'm not sure if that answers your question or just a different question.
Yes, the easy answer is 40 billion light years.
Yeah.
Because that's the time.
Yeah.
14 billion years.
Yeah.
It's the same number. Well, minus the 400,000 years. Can I ask? We're talking about switching on and off supermassive black holes. Actually, I was wondering whether that question comes up or not. What happens if our black hole switches on, and should we be worried?
So that is a fun question, because there was a paper about this actually. So because I talked all about this radiation that outshines the galaxy. So if you turn a black hole in the center of the Milky Way, it would outshine the Milky Way. We are lucky to live in the disk. So because we live in the disk of the Milky Way, we kind of sit in the outskirts, so a lot of the radiation would be blocked by the disk itself. There was a paper at some point, which was very amusing, where someone tried to see if the black hole in the center of the Milky Way were to start accreting, would it kill civilizations? And that, I think, concluded yes. But I think we studied it in a very cheerful journal club, and we thought that some of the dust and gas was ignored.
All right.
Yeah.
So that's good news then. All right.
Yeah. I think it will depend on. I think we should be. We are quite far out in the galaxy. It will be extremely bright, but a lot of the radiation will be blocked because there's a lot of dust and gas. So the X-rays that sort of what you'd want to block is the high energy radiation that's going to kill us, and that the gas should do sensibly well, I think.
Good to know. Yeah. On this positive note, is there another question? We have a few more minutes.
Okay, so the black hole in the middle of the Milky Way is not turned on at the moment. How long do you think it would be before it does turn on? Is that a sort of will be turned on at some point?
We don't know. Because we have some amount of warning in the center of the Milky Way, so at some point disrupted more or less peacefully, and there was no start of accretion. It's really hard to say, because most likely a lot of the accretion that would happen in galaxies like that would be just random gas clouds moving towards the center. And I guess that would be kind of hard to predict when exactly that happens. We don't have currently any warning of gas clouds moving towards the center of the Milky Way. But it's going to turn on at some point. Yeah.
It must have quite a lot of stars surrounding it at the moment anyway, so wouldn't it start pulling those in?
Well, they'd have to get close enough to actually get tidally disrupted. So basically, to actually disrupt a star around a black hole, it has to get quite close, because basically, if you remember that curve of the gravitational potential, basically, quite similarly, there'll be, what you'd want to happen, well, okay, there's two parts. If it just gets swallowed, it would just get swallowed, there'd be no radiation, right? If it just gets swallowed whole, it gets swallowed whole. There'd be one less star to observe, but otherwise we wouldn't see a change. What we'd see is if it would get tidally disrupted, so basically ripped apart by the tidal forces of the black hole, in that case we might form an accretion disk. But still, a single star is not a lot of mass. So some of the good black holes, if they're accreting at maximum efficiency, they will consume about a solar mass per year in their accretion disk. So there's a lot of matter in those accretion disks. So a single star doesn't really do a lot. You'd need quite a lot more to form a nice, efficient accretion disk.
I think we're safe. For the next few million years. We'll be crashing to Andromeda in a few billion years. But that's all right.
Oh, right, I forgot about mergers. How could I forget about
all right. Well, it's a fascinating topic. I think we could go on for a long time. Thank you so much, Caroline. Safe journey home.